Hey, scholars, welcome to Chapter 9. Um, this is the last chapter we're covering for the semester. So I'll tell you what, let's go ahead and get going. All right, so this is going to cover a lot of the same ideas that we covered in Chapter 8. It's just going to apply to the case where we're working with two samples instead of just one sample. All right, so let's get going. All right, so the objectives are largely the same. Key terms are largely the same except for these two here in that are in bold. All right, so this dependent variable and independent variable. All right, so since you're working with two groups, all right, instead of just one sample, you're working with two samples. All right, it creates a situation where we have a independent variable and a dependent variable. So we'll talk about that for a few minutes. Okay. Uh, let's see. Um, now, again, all the parts of the hypothesis test that we covered in Chapter 8 apply here. Okay. Um, the statement of the null alternative, we'll talk about those real quick. The alpha level power analysis, all those are pretty much the same as what we covered in um, Chapter 8. Okay. Testing assumptions, pretty much the same stuff. All right. Um, and again, conducting the hypothesis test, making a decision. All right. Largely the same, with slight variations since we're working with a two-sample t-test. Okay. All right. So again, values for T and DF calculated a little bit differently, but the interpretations are the same. But there are a few other things that we need to consider. All right. All right. So in terms of independent and dependent variables, you've probably heard about these concepts before in your high school or perhaps in previous math classes. All right. But it's a pretty straightforward thing. Okay. The independent variable, all right, causes variation in another variable. All right, and in statistics, you'll hear this variable referred to sometimes as the explanatory variable. So it explains variation in some other variable. Okay, or it's sometimes referred to as a predictor variable. In other words, a change in the independent variable predicts a change in some other variable or the dependent variable. Okay, right? So if you take advanced courses in statistics, you'll normally hear one of these two terms, right? Explanatory variable or predictor variable. All right, the dependent variable, sometimes called the test variable or sometimes called the response variable, right, for the t-test, right, is a variable whose variation, so change in this variable, is caused by some other variable. Okay, so it's the response to, change in the dependent variable is a response to some change in the independent variable. Okay. All right, so one thing you want to remember for a two-sample t-test, the independent variable is always a categorical variable with two values, okay? All right, so I have some examples here for you. You can go with gender, family structure, whether it's two parents or a single parent, or whether it's, uh, you know, it's a household with kids or a household without kids, right? There are a number of different ways, a number of different dimensions to family structure you could be talking about, okay? Marital status, very simply, maybe we're comparing just two groups, the married group and the divorced group, all right? We're comparing them on some thing, all right? And we're saying that whatever this thing we're comparing them on is, it is the product, it is the outcome, it's the result of marital status, right? So people who are married, because they're married, they experience something, you know, to this degree. Divorced people experience it to a worse degree or lesser degree. All right, just sort of depending upon what we're focused on. Okay. All right, then income level, we might have something like this. We'll say we'll take you know, a person's income in dollars and cents. So we'll essentially take it from an interval ratio variable and create a categorical variable based on that. And so we'll say, all right, this person's income is above poverty. This person's income is below poverty, and then we'll go on and make a comparison about what are the outcomes. What sort of difference in outcomes should we see between people who are above poverty and people who are below poverty. Okay. All right. The dependent variable in a t-test, in a two-sample t-test, is usually the interval or ratio type. Okay. Um, So here we have income again, but this time we're measuring it as a dependent variable. So this time it's measured in dollars and cents. All right. So it's not a categorical variable. All right, but measured in dollars and cents. All right. Weight in pounds or ounces, the crime rate, number of courses, number of course units completed, so on and so forth. All right. It could represent a proportion, though. The dependent variable could represent a proportion. So the proportion of people who want lower taxes, for example, or the proportion of people who've experienced this, the proportion of people who think this. All right. Um, so it could be a proportion. All right. Right. So in most cases, the variable that should be treated as the independent variable or as the dependent variable is almost self-explanatory. It's kind of like obvious on its face, but sometimes it's decided by theory. All right. So I might have, as the example I give you here, I might have a theory that says that higher educational attainment leads to higher income. Okay. Um, and, I would say that educational attainment might be dichotomized. So, we'll take educational attainment and convert it to two values, right? They've completed college or they have not completed college. All right. And so then we would go compare the incomes of people who completed college versus those who haven't completed college. All right. And so according to my theory, the people who've completed college should have higher incomes. All right. Okay. So, but there might be some condition under which, we need to reverse the roles of of income and education. So instead of educational attainment being the independent variable, it becomes the dependent variable, right? Higher, income, instead of being the dependent variable, it becomes the independent variable. All right. So educational achievement and higher income in this different situation will switch positions. Okay. All right. So we might say something like this. What if we're looking at educational achievement among children? All right, well, children who come from a household with a higher income will probably go further in their education than children from families with a lower income. All right, and again, folks always remember, when we make these statements, we're talking about averages. We're not talking about absolute differences. Okay, so we're not saying, you would never say that, well, every kid coming from a wealthy household will have more education than a kid coming from a poor household. All right, that's you know that's just not true at all. Okay, so we're always talking averages. All right, but nevertheless, all right. Sometimes it's a matter of theory. how you assign variables as either independent or dependent. Okay. All right. So the null and alternative hypotheses are, look much the same. All right. Except here there's no specific value that's being stated here, or at least not explicitly stated. It's rather implicitly stated. So here we're essentially saying that the null value is 0, all right? Because we're saying that in the case of a mean, the mean for group 1 is the same as the mean for group 2. So we said we could also say the mean for group 1 minus the mean of group 2 is equal to 0, right? No difference. All right. Here we're just simply saying the two groups are, the two group means are not the same. Here in similar vein, we're saying that the proportion for group 1 is the same as the proportion for group 2. All right. The proportion for group 1 is different from the proportion for group 2. All right. All right. So again, not too much different from what you would see in the single sample t-test. All right. Like the single sample t-test, the samples in a two-sample t-test are assumed to be randomly drawn from a population, a well-defined population. The samples are sufficiently large, and in some case, and usually what we want to see is that the two groups have, if not the exact same size, roughly the same size. So we don't want one to be just enormously large and another to be kind of small, right? We want them to have roughly the same size. Okay, so they don't have to be the exact same, but we want them in the same size range. Okay. The dependent variable is interval ratio, or again, it could be a proportion, right? And then the independent variable is categorical, all right? Again, folks, only two values since we're only working with a two-sample t-test, okay? And the dependent variable is normally distributed in both samples, all right? So you see the echoes, all right, of the assumptions applied in the single sample t-test. Okay. Now, there is one set of considerations we have to take into account for the two-sample case, all right? And that's whether our samples are independent samples or they're paired samples, all right? Because that will change some things about how we run the test, okay? Another thing that will change some aspects of the test would be this, the second bullet point. Do the samples have the same variance? So we can look at the standard deviations in both samples. If those are the same, okay, then we would say they have the same variances, and we would sort of modify our test for that situation. All right. If they have different variances, there are some other things we have to do differently, okay, to the test in order to account for some things. All right, so we'll talk about those two things next. All right. So briefly, two samples are independent if selection into one sample doesn't influence selection into another. All right, so if I wanted to just compare two groups of people, well, we'll say, I wanted to compare women and men on some dependent variable, right? I don't know, educational attainment, income, height, weight, whatever, okay? All right. When I draw a male from the sample, from the population, all right, the selection of that male should not influence the selection of a female, right? That shouldn't happen. those uh, those two selections should be independent of each other. Okay. All right. Now, I mean, there are some cases under which I want selection of one uh, man to, influence the selection of a woman and vice versa, right? But in most studies, you're looking at independent samples, right? Independent selection, okay? Paired samples, all right, is where selection of of one person into the sample um, leads to selection into a second sample, leads to a selection of someone else into a second sample, all right? And typically, um, where you see paired samples are in what we call longitudinal studies or panel studies, where we might follow a group of folks. All right, so we take one sample from the population, and then we take some measurement at time one of that sample, and then we come back to that same sample maybe a month later or 2 months later or a year later or however long, okay? And then we ask them, maybe the same set of questions or take the same set of measurements from them. All right, so we treat those as two different samples, but they are paired samples because in order to be in the second sample, you have to be in the first sample, right? Right. So in order to get the measures at time two, you had to be in the sample where we took the measures for time one. Okay. All right. So in that case, you're working with paired samples. Okay. Selection into one influences selection into another. Okay. All right. And here's just like a simple graphic of the paired samples case. So, these are the same groups. All right. Except we have the group at time one, and we take some measure, maybe how happy they are, or whatever. And then we come back to them at a later date and say, all right, how happy are you now? Okay. All right. And typically, uh, between time one and time two, they're subjected to some sort of stimulus. Okay. And then we want to mark the change in that, the change in their, happiness or whatever after exposure to that stimulus. Okay. So paired samples in a longitudinal study. That's, you want to remember that for the quiz. Okay. And the only reason why I use longitudinal studies is because, well, there are a couple of reasons why. One, it's pretty easy to kind of understand why these samples will be paired, right? But mostly I focus on longitudinal studies because I specialize in longitudinal research. Okay. All right. And then the assumption of equal or unequal variances. All right. So the reason why this is important is because this first bullet point right here. Some of these tests that we set up for differences between two groups or differences between 3, 4, 5, however many groups, these are sensitive to differences between sample variances. All right, so if one sample has a pretty small standard deviation and one sample has a very large standard deviation, that could cause some problems. All right, and it could lead us to commit either a type 1 error or a type 2 error. So remember, a type 1 error is when we reject the null, but the null is actually true. Okay, so we reject it as false, but the null is actually true. Type 2 error is where we fail to reject the null, so we assume that the null is true, but the null is actually false. So we fail to reject the null, but we should have rejected the null. Okay. All right. So it might lead us to make a type 1 or type 2 error, and of course we want to avoid both of those like the plague. All right. All right, just a note here. SAS and other statistical software programs, have multiple ways of, testing for equality of variance. Okay, and in pretty much all of the tests, I can't think of a test that's different, but I'll say, just in case there is some test out there that's different, pretty much all of the tests run with this null hypothesis. All right, so the null hypothesis for these tests, certainly for these, states that the two samples that we're comparing have equal variances. Okay. All right. So there, the p-value will tell you, well, all right, reject the null or accept the null. Okay. All right. And at the very end of this lecture, we'll just give you a brief example of the effect of large differences in variances on test results. All right. All right, we'll go through the equations, but again, just remember SAS is going to do all this for you, so you don't have to worry about calculating these by hand or anything like that. The important part here is just to kind of show you, all right, what these equations look like. All right, and this is for the mean, for the test of differences in means. All right, so note the numerator here. All right, so we have the mean of group 1 minus the mean of group 2. All right, and this represents what we see in our sample. Okay, the second term represents the null. All right, so the mean of group 1 minus the mean of group 2. All right, this is the null condition. All right, now the null, remember that the null hypothesis says that the two groups are the same. Okay, all right, so this term reduces to 0, and so we can just kick it out of the equation. All right, and we can reduce it to this. All right, so the mean for group 1 in the sample minus the mean for group 2 that we see in the sample, right, divided by the estimated standard error of the difference in means. Okay. All right. And the equation below is for the calculation of the estimated standard error of the difference in means. Okay. All right. So again, you don't have to worry about calculating these by hand. All right. SAS is going to do everything for you. All right. Same thing here. All right. So for the T for proportion, is the proportion for group 1 minus the proportion for group 2 divided by the estimated standard error of the proportions. Okay. All right. So you'll see all these numbers in the SAS output. And remember, folks, that there's going to be a lot of numbers that SAS shows you, but you want to just keep in mind that there are only just a few numbers you need from the output. All right, just a few. All right. Of course, like the single sample t-test, we have a degrees of freedom calculation that goes into this. All right. And as I have here again, SAS will do all this for you. But take note of the fact that when we have equal variances, we have one equation for DF. If there are unequal variances between the groups, all right, well, we need to do a few more calculations, okay, to make adjustments for that difference in variance, okay. All right. Let's see, anything else there? No, I think that's it. All right. I meant to show you this in chapter 8. All right. But here, I just want you to take into account a basic pattern that you see here. So like I was telling you, in chapter 8, fewer degrees of freedom essentially penalizes you, right? And it makes it harder for your hypothesis to pass the test, all right? So it makes it harder for you to be able to reject the null, all right? So if you take a look here, right, at 100, these are all crucial, not crucial values, critical values for t, all right? These are all critical values for t that differ according to the alpha level that you set, whether it's a one-tail or two-tail test, and then degrees of freedom, okay? All right, but generally, let's look at how these numbers change as a function of degrees of freedom. All right, so if you have 120 degrees of freedom, all right, let's say if you set the alpha level at 0.05 or at 0.95, sorry, right? You set the alpha level at 0.95 for a two-tailed test. All right. The critical value for t is 1.96 after 120 degrees of freedom. Okay. So if you have more than 120 degrees of freedom, you can just use 1.96 as the critical value for t. Okay. But if you only have 1 degree of freedom, look at the critical value. The critical value jumps tremendously. Okay. So if you have this critical value, you only need to meet or exceed the value of 1.96 in order to reject the null. Okay. But 1 degree of freedom, you need to have a value. You need to meet or exceed a value for t of 12.706. Okay, in order to reject the null. All right, so it becomes much more difficult to reject the null. Okay. Now, if you want to reject the null at a even larger alpha value, so 0.99 and some change, all right, past 120 degrees of freedom, right, again, the value is still pretty small, 3.29. But 1 degree of freedom in the same condition, right, jumps to 636.619, all right? So again, I mean, way more difficult to pass the test, or way more difficult to reject the null, all right? It becomes way more difficult, okay? So again, more degrees of freedom, easier test, fewer degrees of freedom, penalties, okay? All right. More degrees of freedom, just a better test for the hypothesis overall, right? Right. But fewer degrees of freedom, all right, that means you're using a whole lot of information to, to set this value at a, at a particular level, okay? So you got to pay the price for that, right? All right, you got to pay the price for that, and that's what you see going on here, okay? All right. All right, so in SAS, again, you're going to run all this in SAS, right? Um, you're going to use the Proc Ttest. So Proc Ttest data equal, you have the data set name, and then you have, various options out here. And like I said here, and like we did for chapter 8, right, we can have a alpha value, or, we can tell SAS to give us the confidence limits, and tell SAS if it's a one-sided or two-sided test, or a one-tailed and two-tailed test, right? If we don't have any of this stuff, SAS will go with the defaults. So it'll default to an alpha of 0.95 and assume you want a two-sided test, okay? Because again, a two-sided test is a stronger test of the null, okay? All right, the class variable, or the class statement here, right? This is where you list your independent variable, Okay, so again, this is your variable that has only the two values, all right, and those two values differentiate the groups, all right, that you want to compare. Okay, so the values can be numeric or they can be character. So you could have a class variable called group or groups, something like that, and the values for group can be 1 for first group, 2 for the second group, or it could be A for the first group and B for the second group. All right, but those values can be numeric or they can be character. All right, and then you can have multiple dependent variables. All right, so if you wanted to compare these two groups on a lot of different dependent variables, you can list all those variables here. All right. Again, they could be they're usually interval or ratio variables, but sometimes if you have a categorical variable with dummy values like 0 and 1, right? You can use those dummy values, right? You can use that variable. All right, so even though it has only two values, 0 and 1, right? You can use that to set up the variables that look like proportions, okay? All right, and then you have other options available here, but again, we're going to just run with the simplest setup, all right? All right, so here's what the output looks like. And again, you get quite a few numbers, all right, but you're only looking for a few things. First thing you want to do is start it with this table up top. And then you want to just focus on the descriptive statistics that you see here for group A and group B. So here I have simply team A and team B. All right. So team A has 241 people in it. Team B has 259 people in it. So roughly, the same kind of ranges of sample size, right? The mean for team A is 98.51 and some change. The mean for team B is 110. Okay. All right. So that gives us a difference here of negative 11.6713. Right. So it takes team A, it takes the mean for team A and subtracts the mean for team B. Okay. Note also the standard deviations. All right. Pretty close together in value. Okay. 20.345. and 19.121. All right, so pretty close together. All right. All right, so you want to take note of that. All right, because this goes back to, thinking about equality of variances. Okay, so here it looks like we can safely treat these as the same, right? We could safely run with the assumption that our variances are equal. All right. All right. And then we go to the third table, right? And this gives us all the information for the results of the t-test, all right, for the results of the comparison, all right? So if our groups have equal variances, we can use the top row. If they are substantially different variances, we want to use the bottom row, okay? So the top row pooled, so if the variances are equal, and then the Satterwhite method if the variances are unequal. Okay. All right. So in this case, we have we can treat our two groups as having equal variances. All right. So we'll use the pooled row, right? So pooled equal. We have 498 degrees of freedom. Okay. The t-value is negative 6.61. And again, we use that same equation for t that we covered in a few slides back. Okay. And the probability of the null being true is very small, so it's like 0.0001. Okay. So it's a very small probability, right? So if we want to reject the null, that these two groups are the same, all right? So remember that the null hypothesis states that the two groups are the same, all right? So here it's saying that the probability of the null being true is very small, all right? And if this value is 0.05 or less, right, we reject the null. We can safely reject the null, okay? So in this case, it's way, way smaller than 0.05. So in this case, we can reject the null, right? Which means that these two groups seem to be very different from each other, okay? All right, now this last table down here tells you a little bit more about the equality of variances stuff, all right? And again, this is the folded F test, right? We're not going to go through this because the folded F test uses a different distribution than the normal distribution to evaluate the differences, okay, in variances. All right, so we're not going to worry about going through it here, okay, but you would interpret this PR of F value the same way. If this is 0.05 or less, that means you reject the null. And the null, in this case, says that the variances are equal. All right? So in this case, right, we have a probability of 0.3273. So that's way larger than 0.05, right? Over 27 points, you know, higher than 0.05. All right? So here we say, all right, well, we fail to reject the null. Okay, so the variances of the two groups do look to be the same. Okay, all right, and again, you can kind of see that up here. All right. All right, writing up the two sample t-test results is pretty straightforward. So I'm drawing all these values from the output that I just showed you. Right, so the mean for team A, and then I give, you know, the mean and the standard deviation. Okay, so the mean is 98.52, the standard deviation is 20.35. Right, so the mean for team A is significantly different from the mean for team B. And again, I give that information. And then right after that, just following a comma, I put in information showing the results of the t-test. So I indicate what type of hypothesis test was used, the t-test. I give the degrees of freedom, 498. I give the value that was calculated for the differences in the means, and then the p-value. All right, and again, it's sufficient when you have those really small p-values, like, you know, 0.0001. Okay, it's sufficient just to say, you know, the p is less than 0.01. Okay. All right. Let's see. All right. So I did want to show you how differences in variance could, you know, it can affect the outcome, right? So I'm using the same data, okay, all right, except here I have well, I'll say this, I'm using the same samples, but I've rerun the simulation, right, using different standard deviations. All right, so for group A, for team A, I still put in, you know, give me a standard deviation of 20. All right, but for team B, I jacked it up to 80. All right, so it shows here a standard deviation of 76. Okay, that reflects that larger standard deviation that I requested in SAS. Okay. All right. But, you know, looking at the size of the differences here, okay, so when you see something, when you see that the standard deviation for one group is about 3 or 4 times larger than the standard deviation for the other group, All right, that's when you need to start thinking, all right, well, maybe we should not treat these two groups as having the same variances, okay, because clearly they are different. All right, and look at the effect that it has. Okay, so remember, the values of t in that first example, right? When we had the very similar variances or very similar standard deviations between the two groups, okay? Right? We had a t-value of like negative 6.61, okay? Now look what it is. It drops by almost 2/3, all right? All right. And then look at the value that we get for the PR of t. All right. This is a way larger. All right. It's still less than 0.05, but it is way larger than what we saw in that first set of output. Okay. Now this is all being driven by that fairly large increase in the standard deviation just for team B, right? Didn't really change much for team A, right? Right, but for team B, right, really large jump. Okay. Now, we might say in this case, well, no harm, no foul. We still come to the same conclusion. We can still reject the null in this case, right? And even in the Satterwhite case, we can still reject the null. But you got to think about the effect that that larger standard error has had, right? Because there might be some cases where it does make a difference. It does cause a change in the conclusions, okay? So in this case, what we could say is that, well, this larger standard deviation, or this larger difference in standard deviations, essentially increases the probability that we observe, and it decreases the t-value. All right, so in summary, what we have here is an increase in the likelihood of making a type 2 error. Right? So if we say that the previous analysis is the correct analysis, then we should reject the null, right? But in this case, this is telling us that, well, yeah, we can still reject the null, but as that standard deviation increases, right, it's pushing us towards a type 2 error. Okay? All right. Let's see, what else we got here? All right, so that's it. Okay, so now you're ready for gear 2. I'm sorry, for gear 3, and we're going to take you through the process of doing something very similar to what we just did here. Okay, it's all going to be based on a 2-sample t-test, and then we're going to write up the results and go from there. Okay. All right, but one thing before we go, this is the last gear project for the course. You have, the quiz for Chapter 8 is the last quiz for the course, and the lab for Chapter 8 is also the last lab for the course. Okay, so everything is going to be posted very soon. All right. Let's see, anything else? Okay, I think that's it. All right, go ahead and take a look at the gear.